Hello, everyone, and welcome back to the Cisco Optics Podcast, where we talk about optics for networking. What are the industry's technical experts in pluggable optics thinking about today? What are the technical boundaries that the smartest minds are pushing past to make the next generation of high-speed optics? If you're wondering about this, we have just the person for you. This is episode 7, where we continue a conversation with my esteemed colleague, Mark Noel. Dr. Noel is a Cisco fellow, and for good reason. In my 8.5 years at Cisco, I've known him to be a highly respected and influential leader not only at Cisco, but the entire optics industry. In this third part of our 4-part conversation, we continue talking about thermal considerations, which he's been thinking and writing about lately. Mark Noel is a Cisco fellow in Cisco's Optics and Optical Systems group. His focus is on next-generation interconnect technology innovation to meet Cisco's needs. Mark is also active within the industry standards and forums and has chaired multiple IEEE 802.3 Ethernet projects. He represents Cisco on various industry alliances and consortiums. Mark also chairs a number of industry multi-source agreement groups focusing on next-generation optical module form factors such as QSFP-DD and QSFP-DD800 and optical interface signaling technology like the 100G Lambda MSA. This guy has done it all. If you haven't already, please subscribe to this podcast. It may show up as the Cisco Podcast Network, which has other great podcast series as well. Check out our blog at blogs.cisco.com and search on hashtag Cisco Optics blog, all one word, no hyphen and no spaces. For our YouTube playlist, go to youtube.com and search on Cisco Optics. And for product information, go to cisco.com/go/optics. And now, join me as I talk with Mark Noel.
The other aspect is cost is very important because there's so much of it, especially in the data centers, there's so much of this technology going in to these networks. There's a real focus on the dollars per gigabit out of this. And if you can go leverage, if you can create any kind of economies of scale, that's to your benefit. And that again, motivated us to stay within that form factor.
Yeah.
Right. Leverage what we could.
There's one thing I want to get straight in my mind. We were saying how 10 gig had been around for several years, like 10 years before SFP Plus really needed to happen. In optical transport, we've been doing hundreds of gigabit for years, right? Starting with line cards and then CFP2. Has it just not been around long enough to get the power consumption down, or is it inherently because it's a coherent thing that the coherent technology is just requiring a certain amount of power that's just very difficult to reduce?
That's most of it, right? To go those longer distances requires, before coherent, you had to have a lot of optical components in and around it as well, so they were big and bulky, and lots of quality, high quality and high speed at the time drivers. So all of those things were quite large. And then when the industry shifted over to the coherent technology, which relieved us of having to worry about all of these optical components to compensate for all the fiber effects and allowed us to deal with it all digitally, that was fantastic. But those chips were very large and they're doing a massive amount of processing to unwind all of those fiber effects, right? That's the advantage of the coherent technologies, is you're moving the problem of the optical impairment from an optical world and you're solving it now in a digital world. Mm-hmm. But nevertheless, that chip is still a big, powerful chip. And it was inconceivable that you would even consider putting that chip in anything that was pluggable in the early days. But, again, Moore's Law to the rescue. What used to be a very large, high power chip is now something which is small enough to fit within a pluggable module. Or this is the first generation that's inconceivable, really. And in all fairness, the 400ZR modules that we do have as pluggables, they're not the ones that are going 10,000 kilometers. You still need a bigger processor for those, right? So it's the 400ZR, and this was largely driven by the web scale customers that said they needed a pluggable module that was the same as the other reaches that allowed them to get into about this 100-kilometer range, and that's where the 400ZR came from. And so while we were able to sort of make those chips leaner by throwing out some of the capabilities that, to only do 100 kilometers, it still was quite a powerful chip. And that really is what's pushing the power levels up on these pluggable modules, right? So as a system designer, I need to build my system to support the worst case. And so if a 400ZR module is the worst case at 15 watts or 20 watts, I need to figure out how to cool. I don't know if a customer's going to put in one of those or going to fill the line card with them. So I need to figure out how am I going to go cool independent of where it goes or what it is. If a customer puts in a 20-watt module or puts in all their 20-watt modules or 25-watt modules in there, I need to figure out how to make that work.
Okay. So really basic question here. So power consumption aside, I'm sure there are good reasons to want to reduce just the sheer power usage, but thermally, like why do we care so much about heat for the optics sake? Like why not just let the optics run?
Right. So
at a very high temperature.
Right. So, you're right. No one wants the power, right? We all want the power to be low. But from a performance perspective, the problem is lasers don't like heat. And, for two reasons. As you heat a laser up, its performance degrades. So you just get less and less power out of it and cause it to get hotter, which makes it just becomes a thermal runaway issue. Mm-hmm. And so you have to keep your laser within a certain temperature range in order to just have it perform and generate enough light. And the hotter that you run the laser at, it impacts the reliability. And with these, reliability is crucial in a network. So you're limited to holding in a module. You're limited to holding the temperatures of the internal components at a certain level, or just so that they perform and meet spec, right, and don't fail. So that's a fundamental. That is the fundamental reason we're worrying about this.
So what are the methods used to do this cooling traditionally?
Well, it's very simple, right? We have fans and we blow air, and that's all we do, right? There's a lot of talk about liquid cooling, and there's and I don't want to be facetious because there's a lot of complexity in this, but at the end of the day, we're just blowing air across the components to cool them off. And while there's liquid cooling and lots of great things out there, again, we can't go tell customers you need to go install plumbing in all your data centers and then we'll sell you equipment. At some point they will put in plumbing and we will design our equipment to be ready for liquid cooling. But until that point, we have to solve it with an air-cooled system.
Well, right. Air cooling of the module, right? Inside the module, is there other stuff going on to conduct it?
Well, so the challenge is how do you just get the heat out of the module? The module is generating its heat, and your job is really to just get it out as efficiently as possible. And so in the early days of things like the 10 gig SFPs that you're talking about, we just have a cage. We have a connector on the board, and we have a cage. We call it a cage. It's like a metal canister or a coffin, really, that you slide it into. And the cage does, it holds it in place and it allows you to latch it. And it really is a little oven, right?
And it makes thermal contact with the
in the early days, no. It was literally just just a hole, and the module would just heat within that, and there would be air blowing near to the cage. But the powers that we were dealing with, so if it was a 1 watt SFP or a 3.5 watt QSFP, the heat would dissipate into the cage, and it would dissipate into the air surrounding that, and there was airflow around it. But we didn't do anything more than that. And what has changed is once we said, okay, I'm not solving a 3.5 watt problem here, I'm solving a 25 watt problem. All of the innovation has happened around optimizing that cage design and figuring out how to put heat sinks next to the module so that all that heat gets drawn out of the module into the heat sinks, and then the air, takes it away. And therein lies the OSFP versus double density split. Because the double density, QSFP double density, said we can't change the form factor, therefore we have to live with this flat top module as it is. And OSFP said, hey, this is going to be too hard a problem to solve. Let's make the module bigger and let's integrate a heatsink onto it, because having an integrated heatsink is far better in terms of thermal conductivity. You don't have to worry about metal to metal contacts. And so, solving this 25 watt problem with a QSFP DD was considered by some impossible to do. We didn't think so.
Aren't there always going to be naysayers? Like even, I think I heard that back with 10 gig SFP plus, people were saying, the circuit traces are just not going to be able to support the 10 gig signals.
Yeah.
But then, smart people figured it out.
That's as I said, you give engineers a problem and they'll solve it, right? And the techniques that we use to build those equipment 10 years ago and 20 years ago is totally different to how we do it today. And it's exciting to see what we're going to be doing in another 10 years.
So as part of this MSA, you're designing this. That was the third part of my conversation with Mark Noel. Next time, we'll continue our conversation on thermals, including system-level considerations, and let you know where you can get technical guidance on thermal design for QSFP DD modules. Subscribe to this podcast, and we'd really appreciate you helping to get the word out. Share this with friends and colleagues that come to mind when you think of network technology and optics, and leave a review on Apple Podcast, formerly known as iTunes. We're also on all the other major podcast platforms. You may see the Cisco Podcast Network come up when you search for Cisco Optics Podcast. That's where we live, and you can find other great podcasts there too. Also, check out the Cisco Optics blog at blogs.cisco.com and search on hashtag Cisco Optics blog. No spaces and no hyphens. We also have educational videos on YouTube. Just go to youtube.com and search on Cisco Optics. Thank you for listening. This is Pat Chow, Product Manager at Cisco Optics. The next episode is part 4 of my conversation with Mark Noel. Until next time.